Right now, engineers are designing machines that have never existed before. Robots that will crawl across craters, hop over ridges, and lay the groundwork for something that sounds like pure science fiction. The first city on the moon. And the wild part? The construction has already begun. Not up there, but right here on Earth, in labs and factories where the future is being assembled piece by piece. Stay with me because what these machines are capable of will genuinely blow your mind. Let us start with a question that sounds simple, but actually reveals everything. Why the moon? And why right now? The answer goes way deeper than national pride or space race nostalgia. The moon is sitting roughly 240,000 miles away, which in cosmic terms is basically next door. It is close enough that a radio signal takes only about 1.25 seconds to get there. That proximity matters enormously. It means humans can communicate with machines on the lunar surface in something close to real time, at least compared to Mars, where a signal can take between 3 and 22 minutes, depending on where both planets are in their orbits. The moon is essentially our training ground, our proving ground, and potentially our first permanent address away from Earth. But here is what most people do not realize. The specific location that space agencies are targeting is not just anywhere on the moon. It is the South Pole. And this region is unlike anything astronauts explored during the Apollo missions back in the late 1960s and early 1970s. The South Pole is home to some of the most extreme contrasts imaginable. Certain ridges and elevated areas catch sunlight for extended periods, making them ideal for generating solar power. Meanwhile, just kilometers away, deep craters have sat in complete, uninterrupted darkness for billions of years. The sunlight has literally never touched the floors of these craters. And inside that frozen darkness, scientists believe enormous quantities of water ice are preserved. Think about what water ice on the moon actually means for building a city there. It is not just drinking water, though that alone would be revolutionary. Water molecules can be split into hydrogen and oxygen through a process called electrolysis. Oxygen becomes breathable air. Hydrogen and oxygen together become rocket propellant. So suddenly the moon transforms from a barren rock into a cosmic fuel depot, a waypoint where spacecraft can resupply before heading deeper into the solar system. Mars missions could become dramatically more feasible if ships can refuel at a lunar base, rather than hauling every ounce of propellant from Earth's gravity well. The economics of space exploration change completely. But getting to that water, building that infrastructure, and eventually constructing something worthy of the word city requires solving a cascade of engineering problems. And this is where the machines enter the story. The first challenge is simply understanding the terrain well enough to land on it safely and repeatedly. When a spacecraft descends toward the lunar surface, its engines blast the ground with enormous force. On Earth, atmosphere cushions and slows debris. On the moon, there is no atmosphere at all. Dust and particles eject outward at tremendous velocities. And lunar dust is not soft and harmless like beach sand. It is sharp, abrasive, and electrostatically charged, meaning it clings to absolutely everything. Solar panels, camera lenses, mechanical joints, spacesuits. Early robotic missions are specifically designed to study how the surface responds to landing events, mapping safe zones and identifying where future cargo deliveries can touch down without destroying the equipment already there. Then come the rovers, and these are nothing like the lightweight buggies that Apollo astronauts bounced around in during brief surface excursions. Those vehicles were essentially sophisticated golf carts designed for short trips lasting hours. The new generation of lunar terrain vehicles is engineered for an entirely different scale of operation. They need to function for extended durations, cover meaningful distances across genuinely hostile terrain, carry astronauts and heavy payloads, and critically, continue operating autonomously when no humans are present. A rover parked outside a lunar habitat needs to be ready to move, collect resources, or respond to commands from Earth without anyone climbing in and turning a key. These vehicles are mobile infrastructure. Consider the environment these machines must endure. Temperature swings on the lunar surface are violent by any standard. In sunlit areas, surface temperatures can exceed 120 degrees Celsius. In shadowed zones nearby, they can plummet to minus 170 degrees Celsius or colder. Mechanical components expand and contract under these conditions. Electronics that work fine at room temperature on Earth can fail catastrophically in such extremes. Every material choice, every circuit design, every seal and joint must account for this punishment, and must account for it across months or years of continuous operation, rather than just a few days. Beyond rovers, one of the most fascinating categories of machines being developed for lunar city construction is hopping robots. Standard rovers have an obvious limitation. Wheels need ground to drive on. Steep crater walls, unstable slopes, and boulder-strewn terrain can stop a wheeled vehicle cold. But a robotic scout that uses propulsion to lift off, reposition, and land again can go where no rover can follow. These machines could descend into the permanently shadowed craters to sample ice deposits directly. They could scout over ridges that block line-of-sight communication. They could inspect areas before humans or even rovers approach them. They function almost like aerial drones do on Earth, except the moon has no air, so traditional rotary blades are useless. Propulsive hoppers fill that gap. Now zoom out and think about the full system required to build not just a research outpost, but an actual city. You need power generation at scale, which likely means nuclear fission reactors alongside solar arrays. Because a city cannot run on sunshine alone during the lunar night, which lasts roughly 14 Earth days. You need manufacturing capabilities on the surface, because shipping every brick and bolt from Earth is unsustainable economically. Researchers have been working on techniques to 3D print structures using lunar regolith, the loose surface material that covers the moon, essentially turning the ground itself into building material. Autonomous robotic construction systems could begin assembling habitats before the first permanent residents ever arrive. You need communication networks, because a city requires reliable data infrastructure just as much as it requires physical buildings. Relay satellites positioned around the moon and at strategic orbital points would keep surface crews, Earth-based operators, and autonomous machines connected continuously. You need resource extraction and processing facilities, robotic miners that can excavate ice, separate it into usable components, and feed those components into power generation, life support, and propellant production systems. This is circular economy thinking applied to a world 240,000 miles away. The progression follows a clear logic. Scouts map the territory, cargo landers deliver equipment, rovers establish mobility and begin surface operations. Hopping robots probe the most dangerous zones. Automated construction systems begin building. And eventually, humans arrive not to visit briefly, but to stay and build on everything the machines established before them. What makes this genuinely historic is the shift in mindset it represents. Every previous human mission beyond Earth has been designed around the question of, how do we get there and get back safely? The question being asked now is fundamentally different. How do we stay? How do we build systems that persist, grow, and sustain human life indefinitely on another world? Answering that question on the moon, where help is only a few days' travel away and communication is nearly instantaneous, gives humanity the knowledge needed to eventually answer it on Mars, and perhaps beyond. The first city on the moon will not be built by heroic astronauts with shovels. It will be built by machines, layer by layer, system by system, in the dust and silence of a world that has waited billions of years for this moment. The rovers, the landers, the hoppers, the printers, the miners. These are not supporting characters in the story of human expansion into space. They are the main characters, and their work has already started.